In this coursework, we want to design a 110 volt amperes step-down transformer with primary voltage of 110 to 11 volts with steel magnetic core materials. For designing this transformer, we chose a single phase shell type transformer. It's shell type transformer with the winding on the center leg, and this core type transformer. We use shell type transformer for this coursework. The transformer ratio is 0.1. The single transformer with V2 on top of V1. The number of turns for secondary and primary part will be as the transformer ratio. So first of all, we calculate the transformer ratio. It is 0.1, and we will calculate the current of the transformer. It is 110 volt ampere apparent power, and the voltage is 110. So the current will be 1 ampere. To select the number of coil turns, we have two limits. First of all, we need to design the conductors of each coil as the steel core should not be saturated. So the number of turns must be enough to prevent saturation in the iron core. The second limit is the core window should have enough space for coils conductor. So first of all, we have to choose a standard core and then design the winding. For our power, we will choose a core with size about 96 millimeter. So from a standard EI core producer, we choose a table of the sizes, standard sizes, and we choose number 9 row with 94 millimeter of A and 56 millimeter of B. So we have the area of EI core. Now let's see how to design transformer winding turns. To design winding, we have some references that have formulas to calculate the number of turns. In this paper, it has a formula that we used for turn per volt will be equal to 1 on top of 4.54 cross frequency cross maximum flux density cross the area of the transformer core. So we use this formula to calculate the number of turns. As we know, the turns per volt is like this, and we change the shape of formula to V is equal to 4.44 cross number of turns cross frequency cross maximum of the flux density cross the area. So we know all the materials that we need. We know that voltage is 110, frequency is considered as 50, and maximum of the flux density will be equal to 1.5 teslas. The core that we choose has 784 millimeter area, and so the number of the primary core can be calculated as 421. And we know the ratio of the transformer. The ratio of transformer was 0.1, and the secondary coil winding will have 42 turns. Now we have to check the second limit. We know that our turns will be 42 and 421. The second limit was the core window should have enough space for our coils. We know the number of turns. We can calculate the window area and check the area of each conductor. Each coil cross-section area will be equal to the window area divided by 2. We can't use all the window area. We have something called fill factor, the area that we can actually use. So we know that copper area will be equal to fill factor cross the real area. For a nominal fill factor, I think 0.75 is good. And we have the real area for the coil. So our copper area will be 220 millimeter. As we know the number of turns, we can calculate the each conductor area. The wire area will be equal to 220 divided by 421. And we can calculate the wire diameter easily. So let's check the current density in our transformers. The allowable value of current density for small power transformers are taken as 1.5 to 2.6 ampere per millimeter. So if we use the maximum current density for this transformer, we can calculate that our maximum allowable current in our transformer is 1.636 amperes, which is higher than rated power of the transformer. So our design is okay for this amount of volt amperes. The design of transformer is finished. We have an EI iron core, as we can see in the picture, and we will have 421 turns for primary coil winding and 42 turns for secondary winding. It was 2. Here the transformer design is finished, and I think it's very good to simulate this design in softwares like Ansys, Maxwell,